Hello everyone. Today's topic is Raman scattering. What is meant by Raman scattering? Consider a monochromatic radiation having frequency nu 0 is allowed to incident on transparent solid, dust-free liquid or gas. Then a fraction of the incident radiation is scattered. Most of the scattered radiation has the same frequency as the incident one. In the figure, it is represented as the Rayleigh line, which has the same frequency nu 0 as that of the incident frequency. However, a few are scattered with a difference in frequency. A few means 1 in 10 raised to 6. This is represented as anti-Stokes lines or Stokes lines. This phenomena we will call it as Raman scattering. Now the scattering without change in frequency is called Rayleigh scattering. Now we have a Rayleigh line which has the same frequency as that of the incident frequency. But there are weak lines. Of modified frequency on either side of the exciting line or Rayleigh line that are called Raman line, and the frequency shift is called Raman shift. If you see, there are anti-Stokes lines and Stokes lines. Stokes lines having lower frequency, anti-Stokes lines having higher frequency compared to Rayleigh line, and here delta nu is called the Raman shift in frequency. The lines having frequencies on the low and high frequency side are called Stokes and anti-Stokes line respectively. This means that Stokes lines having lower frequency compared to the exciting line or Rayleigh line, and anti-Stokes lines having higher frequency compared to the Rayleigh line. Let us discuss the mechanism of Raman effect. Mechanism of Raman effect. Suppose a beam of monochromatic light having energy h nu 0 is incident on a solid, then we know that there will be scattering. The scattering are of two types. One is elastic scattering and another is inelastic scattering. In elastic scattering, the energy of the molecule is the same. The molecule neither gain or lose energy. Suppose a monochromatic radiation of energy h nu 0 is incident on the molecule. The interaction happens and there will be scattering. Since the molecule does not absorb or lose energy, the scattered photon has the same frequency as that of the incident frequency. The frequency of the scattered radiation is nu 0 and the frequency of the incident radiation is also nu 0. Correspondingly, you will get a spectral line that is called Rayleigh line. Now, what is inelastic scattering? In inelastic scattering, the molecule is either gain energy or lose energy, and depending upon that, we have absorption and emission. In absorption, the molecule gain energy, whereas in emission, the molecule lose energy. Let us discuss absorption first. Consider a monochromatic radiation of energy h nu 0 is incident on the molecule. Now the molecule absorbs a part of the energy from the incident radiation, and as a result, the scattered photon has an energy which is lesser than the incident radiation. This is because the molecule absorbs an energy plus delta E from the incident radiation. Therefore, we can say that the scattered photon has an energy lesser than the incident photon. Certainly nu is less than nu 0. Now correspondingly you will get a spectral line that is called Stokes line. Now let us see what happens in the emission process. Suppose a monochromatic beam of radiation h nu 0 is incident on the molecule. The interaction happens, but the molecule will lose parts of its energy to the incident photon. Suppose the molecule is in some excited state, then it will emit or it will lose some of its energy to the incident photon, so that the scattered photon has an energy which is greater than the incident photon. Therefore, nu is greater than nu 0 here. Now you will get anti-Stokes line here. You will get anti-Stokes line. The next topic is classical description of Raman scattering. Consider a molecule which is placed in an electric field E. Then this electric field will distort the electronic structure and polarizes the molecule. So we can say there is a polarization induced. This induced polarization is proportional to the electric field. So you can write mu is equal to alpha E. What is alpha? Alpha is the polarizability of the molecule. The induced polarization mu is equal to alpha E. Here we have taken static electric field. Now you consider the situation, the molecule is interacting with a monochromatic beam of radiation h nu 0. Now actually the molecule is interacting with the electric field of the electromagnetic radiation, that we can represent it as E is equal to some E0 sine 2 pi nu 0 t, and as a result the induced polarization becomes mu is equal to alpha E0 sine 2 pi nu 0 t. So what is the consequence? We can say that because of this time varying electric field, the electron cloud will oscillate back and forth, or we can say the induced dipole also undergoes oscillation with frequency nu 0. So you have an oscillating dipole. We know that the oscillating dipole will emit a radiation of its own frequency. Here the frequency of oscillation is nu 0. Therefore, it will emit a radiation of frequency nu 0. So when the molecule is interacting with the radiation of energy h nu 0, it is emitting a radiation of frequency nu 0. So you will get a radiation having the same frequency as that of the incident frequency. This is the classical explanation of Rayleigh scattering. But here we have assumed that the molecule is at rest, but the molecule already has some internal motion. This internal motion can be either vibration or rotation. The molecule is not at rest. And due to this internal motion, what happens? There is a change in polarizability of the molecule. There is a periodic change in the polarizability of the molecule. So the polarization alpha is not a constant. It is some alpha 0 plus beta sine 2 pi nu vibration t. Here we have assumed that the molecule is internally vibrating with the frequency nu vibration, which is actually changing the molecular polarizability periodically. What is alpha 0? Alpha 0 is equilibrium polarizability. Beta is the rate of change of polarizability with vibration. And nu vibration is the vibration frequency of the molecule, which changes the polarizability. Now we have two equations. Substitute 2 in 1. Then rearrange the term. We have mu is equal to alpha 0 plus beta sine 2 pi nu vibration t E0 sine 2 pi nu 0 t. This is equal to alpha 0 E0 sine 2 pi nu 0 t plus beta E0 by 2 cos 2 pi nu 0 minus nu vibration t plus minus cos nu 0 plus nu vibration t. Here we have used a standard trigonometric relation. Now what is the conclusion? The oscillating dipole has a frequency component not only nu 0 but nu 0 minus nu vibration and nu 0 plus nu vibration. This nu 0 corresponding to Rayleigh line, then nu 0 minus nu vibration corresponding to Stokes line, and nu 0 plus nu vibration corresponding to anti-Stokes line. Thus the oscillating dipole has a frequency component nu 0 plus or minus nu vibration. So what is our conclusion? For the molecule to be Raman active, a molecular rotation or vibration must cause a change in molecular polarization. This is the conclusion. The next topic is quantum theory of Raman scattering. Consider monochromatic radiation of frequency nu 0 interacting with a system. The photons undergo collision with the molecules of the system. We can say that the molecular system interact with the radiation and make a transition to a virtual state. There are three cases which is represented in three figures. In the first figure, it is drawn that the molecular system, in the first figure, it is shown that the molecular system absorb h nu 0 amount of energy and undergo a transition from the ground level to the virtual level. And in figure B, the molecular system absorb h nu 0 radiation. Again, it undergo a transition from ground level to virtual level. Whereas in figure C, the molecule already in an excited state, it absorb an amount of energy h nu 0 and undergo a transition from the excited level to the virtual level. So there are three cases. Now let us consider figure A. In figure A, as I specified, the molecular system absorb an amount of radiation h nu 0, undergo a transition from ground level to virtual level, then it returns to the original state by the emission of the same amount of radiation. That is, we can say that the collision is perfectly elastic. No energy transfer takes place. The molecule does not absorb an amount of energy, resulting in scattered photon of frequency nu 0. Correspondingly, you will get a spectral line that is called Rayleigh line. In figure B, the molecular system absorb an amount of radiation h nu 0 and undergo a transition from the ground level to virtual level, but from the virtual level it returns to the state of higher energy. Suppose the molecule absorb a radiation of energy h nu m during the process, then it is clear that the scattered photons has a frequency 0 minus nu m, or we can say the scattered photons has an energy which is lesser than that of the incident photon. Here the collision is inelastic. Molecule gain h nu m amount of energy. So the scattered photon will have the energy h into nu 0 minus nu m. Correspondingly, you will get a spectral line that is called Stokes line. Now in figure C, the molecule already in the excited state, it interact with the radiation and it undergo a transition to the virtual level. Then it loses an amount of energy h nu m, which it already have. Then it returns to the ground level, and during the process a radiation is emitted whose energy is h into nu 0 plus nu m. Here also we can say the collision is inelastic. Here the molecule loses h nu m amount of energy. So the scattered photon will have the energy h into nu 0 plus nu m. The energy of the scattered photon is higher than the incident radiation. Correspondingly, you will get a spectral line that is called anti-Stokes line. In the figure, nu is equal to 0, 1, 2 are the vibrational levels of ground electronic state. Please note that here delta E must corresponding to the energy difference between two allowed vibrational or rotational states. Correspondingly, you will have the rotational Raman spectrum and vibrational Raman spectrum. The next topic is rotational Raman spectra. We know that the rotational energy levels of linear molecules are Ej is equal to Bj into J plus 1 centimeter inverse, where J, which is a rotational quantum number given by 0, 1, 2, 3, etc. Now the selection rule for rotational Raman spectra are delta J is equal to 0 plus or minus 2. Delta J is equal to 0 corresponding to Rayleigh line. Now consider the transition J to J plus 2. Now for the transition J to J plus 2, what is delta Ej? Delta Ej is Ej plus 2 minus Ej, that is equal to Bj plus 2 J plus 3 minus Bj into J plus 1. That is B into J square plus 5J plus 6 minus J square minus 1. That is equal to B into 4J plus 6. Now let us write the wave numbers of rotational Raman lines. Wave numbers of rotational Raman line. Let nu 0 bar represent the original line's wave number. Let the wave number corresponding to the original line is nu 0 bar. Then we can say nu bar is equal to nu 0 bar plus or minus B into 4J plus 6. Nu bar is equal to nu 0 bar plus or minus delta Ej, which is equal to nu 0 bar plus or minus B into 4J plus 6. Where J is always the lowest rotational states, J represents the lowest rotational state. Here the plus sign represent anti-Stokes lines and minus sign represent the Stokes Raman line. Plus sign refers to anti-Stokes line and minus sign refers to Stokes line. From the figure we can see that the separation between the Stokes line is 4b and the separation between the unmodified line and first Stokes line is 6b. The separation between any two consecutive Stokes line is 4b and the separation between any two consecutive anti-Stokes line is also 4b. But The separation between the first Stokes line and first anti-Stokes line is 12B. The next topic is vibrational Raman spectra of diatomic molecule. The structure of vibrational Raman spectra can be understood on the basis of anharmonic oscillator model. We have studied the anharmonic oscillator model, and based on that model, we can explain the vibrational Raman spectra of diatomic molecule. The selection rule for vibrational Raman spectra is delta nu is equal to 0, plus or minus 1, plus or minus 2, etc. In anharmonic oscillator model, we have seen that the transition energies are given by nu plus half omega e bar minus nu plus half whole square omega e bar xc, where nu is equal to 0, 1, 2, etc. are the vibrational quantum number. Omega e bar is the equilibrium vibrational frequency, and xc is the anharmonicity constant. And we have seen that whenever there is a transition from nu is equal to 0 to nu is equal to 1, we get the fundamental absorption line. It occurs at omega e bar into 1 minus 2xc centimeter inverse. And whenever there is a transition from nu is equal to 0 to nu is equal to 2, we will get the first overtone. It occurs at 2 omega e bar into 1 minus 3xc centimeter inverse. And when there is a transition from nu is equal to 1 to nu is equal to 2, we will get hot band. The wave number corresponding to the hot band is given by omega e bar into 1 minus 4xc centimeter inverse. We know that the Raman scattered lines are of low intensity. Already we have studied that the intensity of the first overtone and hot bands are lesser than the fundamental absorption line, and because of this fact, we can ignore all weaker effects in vibrational Raman spectra such as the overtones and hot bands. So we can concentrate our discussion on the fundamental vibration line only. And we can say that the Raman line would appear at a distances from the existing line corresponding to each active fundamental vibration. That is, the Raman line would appear at a distances corresponding to the fundamental vibrational transition. So we can write nu bar is equal to nu 0 bar plus or minus delta E fundamental, because the Raman line would appear at a distances from the existing line corresponding to each active fundamental vibration, and this is equal to nu 0 bar plus or minus omega E bar into 1 minus 2xc centimeter inverse. Here again the plus sign represent anti-Stokes line and minus sign represent the Stokes line.